Am I audible? I'm not using the headphone right now. Am I audible? Is my voice clear? Minashi, Mazia, Hishma, Noha.
Yes, sir.
Sorry. So in the last lecture, we have finished chapter number 1. We finished Gauss law. Hishma, you were absent in the last class, no?
Yes, sir.
So you have missed few derivations which based on the applications of Gauss law. So first chapter is over. We'll be doing starting second chapter now. Now, second chapter is, it depends upon the first chapter. On the first chapter, we'll be using the concept of electric field only. So if you know what is field, you can do chapter number 2. That's it. So chapter number 2 starts with the concept of work. So if you can remember how we start chapter number 1, we start chapter number 1 through work done or through forces. Chapter number 1 starts through the concept of Coulomb force, Coulomb's law, force. And then we did field. Field was related to force. That electric field was force divided by the magnitude of discharge. This was the expression of field. Field is force divided by the discharge. The second chapter, electric potential and capacitance. This is related to work. Second chapter is related to work. So this starts with the first topic, which is work done in external electric. So that's chapter 2, electric potential and capacitance. So before starting this electric potential and capacitance, tell me something. How would you calculate work done? What is the expression of work done? Alia, how we calculate work done in physics? Noha, how we calculate work done in physics? Good, Alia. See, we have two expressions of work done. This was your class 11 syllabus. Work done is the dot product of force and displacement, which you can further write as it's Fs cos theta. That's work. Work done is Fs cos theta. We use this expression only if your force is constant. This expression is for a constant force. If you have a variable force, then instead of the dot product, we use this integral. That work done is the dot product of force and displacement. So these are the two topics. So we use this expression when your force is constant, and we use this expression when you have a variable force. So for a variable force, we use integrals. For a constant force, we just take dot product. So the second chapter will start with the concept of work. So work done in external field. Work done in external field. Electric. Or we can simply write this as work done in electric. So if you take electric field, this is some electric field, and you put a charge Q in this electric field. Let's take some non-uniform field. It's a non-uniform. Curve means field is non-uniform. The magnitude as well as direction of field can vary. So I take 2 points in this electric field. This is point A, and this is another point B. The separation between A and D is, let's say this is dx. So these are 2 points. One is point C, another is point D. The separation between C and D is dx. I place a charge here. This is dq charge, and this is the field. So Mazia, what happens when we place a charge in some electric field? What happens with the charge when I place it in electric field? This remains at rest, this experiences some force. What happens with this charge? Minashi, what happens when we place a charge in electric field? Yeah. Puneet, what happens when we place a charge in electric field?
सर force आता है.
So this charge experiences a force. So what happens is this field exert a force on the charge. The force acting on the charge is Q. Field exerts force on the charge. The electric field exert force on the charge. And that force is F, which is equal to Q. So due to this field, this charge will try to move in the right-hand side direction. If I try to bring this charge from point C to point D, then we need an external force. If you want to move this charge from C to D, then we need an external force. And that external force will be in a direction opposite to that of F external. So the external force that need to be applied on the charge, external force F external, will be negative of force acting on the charge due to electric field. So you can write that F external is minus of Q. That's the external force. Let's call this as equation 1. Next, I need work done by this force to carry this charge from C to D. Work done by external force to carry charge Q from C to D. Minashi, what will be the expression of the work done?
dw equal to force in
See, from C to D, displacement is dx, and the force is this, F external. What will be the expression of work done, Minashi?
minus QE into dx.
Yeah, good. So work done will be the dot product of external force and displacement. Your external force is this minus of Q. So it's minus of QE dot dx. That's the work. So this is work done for a small path C. Now I need work done from some point A. Let's say I call this as Sorry, internet connection. So we were discussing the work done. So am I audible? My voice is clear?
Yes, sir.
Yes, sir.
So the work done to carry charge from C to D is F external dot dx. F external is minus of QE dot dx. But I need work done to carry charge from A to B. So to work done to carry charge from A to B is integral of F external dot dx, and the limit is from point A, the position vector of point A is RA to R. So this is how we calculate work done, or you can write this as it's RA to RB minus of QE dot dx. So this is how we calculate work done in carrying a charge from one point to another against the electron. So this is work done by external force. Work done by external force. This is external. So this negative sign here shows that the direction in which we are carrying the charge is opposite to that of field. Field is to the right hand side and we are carrying charge to the left hand side, which is shown by this negative sign. Now, what if I ask you to calculate work done by electric field? Work done by electric field. Yashika, this is work done by external force, and this is the relation between force by field and external force. So what will be the relation between work done by field and work done by external force?
Sir, we'll take the negative of it.
Take the negative. See, this is the force by electric field, F, and this is the external force. Both external force and field, force by field, are in opposite direction. So we can say that work done by electric field is negative of work done by external force, which is minus of its RA to RB minus of Q E dot dx. So this negative and negative will become positive. So work done by electric field is integral of RA to RB. It's QE dot. So the difference between work done by external force and work done by field is that of a negative sign. Now, again, back to the same discussion. If field is uniform, if I say that electric field is uniform, so when I say field is uniform, that value of field is not changing with position. You can say it's sort of a constant field. So if I say that field is, this E is constant, this variable is not changing, Jasola, what simplification you can do in this integral? If I say that E is not changing, E is constant.
We can take E out of the integral.
We can take E out of the integral. We can take both Q and E because charge is constant as well as field is constant. So when we take both of them out of the integral, then what I get is minus QE dot integral of dx. It's from R to R. Anshika, what is the integral of dx? Anshika, integral of dx. What is the integral of dx? Ishma, what is the integral of dx? Okay, just note it down, then we'll do this. At least note it down.
So is this the new lesson?
Yes. Have you written up to this force work done?
Yes, sir.
This is the work done by Lect.
Sir, can you scroll up first? Sir, listen.
Can I scroll it, Minashi? Akshata? Can I scroll it?
Yes, sir.
Now see, if electric field is uniform, then I can take this field outside the integral sign. I'm just left with QE dot integral of dx. Hishma, what is the integral of dx? It's just dx. What's the integral of dx? Anshika, integral of dx? Raj. Noha?
X.
Yes, integral of dx is x. When you integrate dx, you get x. Limit is from lower limit is r to upper limit is r. So when you substitute the values, it's minus of q e dot. It's rb minus r. So this is the expression of work done by external force. So the work done by external force is minus of q e dot position vector of point B minus position vector of point. But we can use this expression only if your field is uniform. If your field is not uniform, then you will be using this expression for external field. You will use integral. So this is for the uniform. Note it down. We'll do some
non-uniform field में charge constant नहीं होगा?
In non-uniform field, charge may be constant or variable. Like charge and field are two independent things. When we usually talk about charge, we say that charge is a constant thing. So field and charge are independent. This is field which can be constant or variable, uniform or non. Charge is usually charge is always constant.
Okay.
See, most of the questions that you get on this expression are based on uniform field. There are very few questions on non-uniform field. Most of the questions are on uniform. Now, see, this is field. This field is given. E is I cap plus 2j cap plus 3k cap Newton per meter. This is the field which exists in space. Unit work done in carrying a charge of 2 coulomb from point A to point B. Ishma, is this field uniform or non-uniform? Yes, Ishma. Is this a constant field or a variable? Just tell me. Simple question. Anshika, is this a uniform field or a non-uniform field?
Non-uniform.
It's uniform.
See, this field is uniform. This field does not depend upon x, y, and z. It's a constant field. Say I cap plus 2j cap plus 3k cap. 2 is constant. constant, 3 is constant. Here it's 1 which is constant. I cap, j cap, and k cap are fixed directions. So that means this is a constant field. It's not a variable. That's a constant. Right? This field is constant. So constant means it's a uniform field. You need work done to carry a charge of 2 coulomb from A to. I need work done by external force. So Mazia, which expression you will use? You will use this expression, this equation number 1, or you will be using this equation, the equation number 2. Mazia, which expression you will use to calculate work done? The expression number 1 or the expression number 2? Fine. So I need work done by external force. So the work done by external force is minus of Q E dot. It's RB, position vector of point B, minus RA, which is position vector of point. So see, charge and field is given. Field is this, charge is 2 coulomb. See what's the position vector. The coordinate of point A is 2, 0, 0. That means the position vector of point A is it's 2 I cap. Y coordinate is 0, that means 0 j cap. Z coordinate is 0, that means it's again 0 k cap. Similarly, R B. Minashi, what will be the position vector of point D? Same logic.
3i plus 2j plus 0k.
Plus 0. That's the position vector of point D. I need work done. Work done by external force. Now let's substitute their values. Q is 2 coulomb. And your electric field E is this I cap plus 2j cap plus 3k cap dot. It's RB minus I. So RB is this 3i cap plus 2j cap plus 0k cap minus RA, which is 2i cap plus 0j cap plus 0k cap. So the work done is minus 2. It's I cap plus 2j cap plus 3k cap dot. It's RB minus RA. Bhishma, just subtract these two terms. What will be the final answer? Bhishma, subtract these two terms. What will the answer? Final answer?
I cap plus
Yeah.
2j cap plus 0k cap.
Plus 2j cap plus 0. Now, if I take dot product of these terms, so Alia, what will be the dot product of I cap plus 2j cap plus 3k cap and I cap plus 2j cap plus 0k cap? Just take the dot product of these two terms. Okay, Noah? Right, no, that's correct. Alia, the dot product of these two terms. Anshika, will you try the dot product of these two terms?
Sir, 1 plus
Yes.
4.
The coefficient of I cap is 1, so it's 1 into 1 plus the coefficient of j cap is 2. Here also the coefficient of j cap is 2, so it's 2 into 2. Coefficient of k cap is 3 and the coefficient of k cap is 0, so that's 3 into 0. So it's minus of 2, it's 1 plus 4. So you get minus 10. This is work done by external force. Now, instead of external force, what if I ask you to calculate work done by the electric field? Mazia, what will be the work done by electric field? This is work done by external force, W external. If I ask you to calculate work done by electric field, Mazia, how will you calculate it? Good, Noah. Mehraj, will you try? What will be the work done by electric field?
The integral of Fs cos theta.
Nah.
Or F.
You have work done by external.
The integral. So it's a constant Fs cos FS हुआ सर, इंटीग्रल नहीं होगा.
How work done by external force? You need work done by electric field. A one line thing. Yashika,
Sir, we'll take the negative of work.
Negative.
Then
so it's minus of minus 10. So that will be 10. Good. This is how we calculate work. Good.
सर
Yes.
सर ये इलेक्ट्रोस्टैटिक्स का चैप्टर तो बहुत बड़ा है, तो फिर जेई के लिए मतलब एनसीईआरटी बहुत होती है या फिर थोड़ा सा चाहिए होता
There's a difference. A difference. Few topics. Like in JEE, you have some topics which mix chapter number 1 and chapter number 2. So when we do JEE, then we first complete potential, capacitance, and then we come to those topics. Like in the previous chapter, you calculated field due to a line charge, field due to a sheet. Then you will do potential due to a point charge, potential due to a line charge. In NEET, you will get questions which are combination of those two topics. We'll come to let's at least finish with this potential thing, then we will be discussing this.
है. ओके सर.
Don't worry, when I finish electrostat, I will finish up to JEE. Electrostat means around 20% of class 12 syllabus. More than 20% of class 12 syllabus. Yes, can I scroll it?
Sir, can you explain this question? I didn't get it.
Okay. See, Arpit, when we calculate work done in an electric field. So when you place a charged particle in an electric field, that charged particle experiences a force. If you want to move that charged particle against the field, then you do a work done. That work done is minus of Q E dot RB minus R. That's the expression. At the end of the class, I will explain how this expression comes up. You have missed the first 10-15 minutes now. You will connection issue. So I'll explain it again at the end of the class. Okay.
Okay,
So
sir.
this is the expression that we are using, minus Q E dot RB minus R. For the time being, don't worry about the derivation. We'll do it at the end of the class. So just substitute the values. Your charge is given, it's 2, electric field is given, this is the thing. And the coordinates of A and B are given. If the coordinates is given, that means the position vector is given. The position vector of A is 2i cap, 0j cap, 0k cap, B is this I cap, j cap, 2k cap. I just substitute the values. I guess you won't have any issue in the steps of the calculations.
No, sir, no issue in that.
This formula is an issue. Huh?
Yes, sir, I didn't get that. That was the issue.
Okay. Next question. Next topic. Conservative nature of field, electric field. See, this conservative term was in class 11 syllabus. So when we say some force or some field is conservative, that means work done in that field is independent of path. So electric field is conservative, that means work done by or against field is independent of path. So work done does not depend upon path. This is the conservative nature of field. Work done does not depend on path means if this is point A and this is point B, I ask you to carry a charge from A to B. You can carry this charge through this path. Let's call this as path number 1. You can carry this charge to this path. Let's call this as path number 2. Or you can carry this charge to this path. That's path. In all paths, work done will remain same. So if work done is same, that means your field is conservative. For non-conservative field, work done will change. So work done is independent of path. It depends only on initial and final position. Depends only on initial and final position. This is the conservative field. That work done is independent of path. Work done depends only over the initial position and the final position. That's the conservative field. Now, if I take a closed path, work done in carrying closed path and carrying a charge along a closed path. Is 0. So that means I take this field, this is a conservative field, and I take a charge. I take this charge in a closed path in conservative field. So the total work done will be 0. This is again the property of the conservative field. Work done is 0. How we calculate work done by external force in field? Hishma, what is the expression to calculate work done by an external field, by some external source in field? I'm asking for a variable field. The expression for work done for a variable field. That's it. Saifullah, expression of work done by external force in field.
Yes, minus QE, integral of minus QE dot dx.
Minus Q integral of E dot dx. And if I'm taking a closed path, then put a close word, and this work done will be 0. So this is the work done in carrying a charge over a closed path in external field, and that work done comes out to be 0. Hishma, is it clear this expression minus QE dot dx?
Yes, sir.
This is what we have derived just now. Na? So if it is a closed path, then put a close sign, and the work done is 0. Now what I can do is I can take this minus Q to the right hand side. If I take this minus Q to the right hand side, I got E dot dx is equal to 0 by minus Q. So that is equal to 0. So what I get is this expression, closed integral of E dot dx is equal to 0. Is it work done? No. This E dot dx, is this the expression of work done? Anshika, is it the expression of work
Yes,
done?
sir. Yes, sir.
Work done. Okay. Then what is this Q E dot dx? This is also work done, and E dot dx is also work done.
So it is when we have a closed surface.
No. This will be work done when you have Q, right? Without Q, it's not a work done. Work done is this charge into E dot dx. There is no charge here. Huh? It's not work done. Work done is this QE dot dx. So it's not work done. We call this term as line integral of electric field. Line integral of electric field. For a closed path, is 0. So that's the third property of electric field, that if you take line integral of field means you take field, take a dot product with small path and integrate it over a closed path. Then that line integral of electric field over a closed path is always 0. So these are the three properties of the conservative field. First is work done is independent of path. It does not matter, like from A to B, through which part you are carrying the charge. You can carry charge through any of the path, work done will remain same. Second, work done, if you carry a charge in a closed path, then work done will always be 0. Third, line integral for a closed path is 0. This is very, very important. It's usually a 1-marker question, that what is line integral of electric field for a closed path? That's always 0. It's not enough. Is it clear, Anshika?
Yes, sir.
So can you scroll up for a second?
The starting of this chapter seems very tough. Like starting is conceptually very complicated thing. But once we start potential, then things will get easy. This is easier than chapter number 1. In chapter number 1, you were dealing with vector quantities. In chapter 2, you don't deal with vectors, you deal with scalar quantities. It's easier than chapter number 1, but yes, this initial path is conceptually very strong. So these are basically definitions.
You're done.
But for the derivation, just keep this part in your mind. What's work done? What is conservative field? What is line integral for a closed path? We'll be using those terms in very Now we will start electric potential. What was electric field, Arpit? Arpit, can you define electric field? What was electric field?
Sir, electric field was the area around which the electric properties of matter existed.
Right. So if you have a charge, there is a region around that charge where electric properties of that charge exist. Like if I take a charge, then there is a region around this charge. And within this region, the electrical properties of this charge exist. Means if in this region you bring another charge, then this charge can attract or repel this charge. So the region in which electrical properties of a charge exist, that region is known as electric field. Electric field is a vector quantity. So in one line, electric field represents the region in which the electrical properties of a charge exist. So we can say that electric field represents electrical properties of a charge in vector form. Electric potential do almost the same thing. It also defines electrical properties of a charge. But electric potential is a scalar quantity. So it's like electric field only. But the difference is field is a vector, potential is a scalar quantity. We relate field with force, but we relate potential with work. So what is electric potential? It defines electrical properties of a charge in scalar form. Electrical properties of a charge in scalar. So that is potential. This defines electrical properties of a charge in scalar. It's property of a single charge. Just like field is also a property of single charge. If you have two charges, then each of the charge, each point charge generates its own. It's the property of a single charge. Now, the exact definition of potential is see, if I take a charge Q and I ask you to calculate the potential of charge Q over this point. So to calculate potential over this point, what we do is we choose infinity, which is a point where the effect of field is zero, where field does not exist. So we choose an infinity. We choose a test charge Q at infinity. Then we calculate work done in carrying that test charge from Q to P. So what we do is we choose infinity. We take a test charge Q at infinity. Then we calculate work done in carrying this test charge from infinity to P. So this is the work done by external force in carrying test charge from infinity to P. If I divide this work done by Q, then what I get is the potential at P minus potential at infinity. So infinity means a point where electrical properties of charge does not exist. That is V infinity. So what should be V infinity now? How much is V infinity? What should the value of V infinity? Yes, Hishma. At infinity, the electrical properties of charge does not exist. So what should be the value of potential at infinity, Hishma?
Zero.
Potential at infinity is zero. So we can write that potential at point P is work done by external force in carrying charge from infinity to P divided by the magnitude of the charge. So this is the potential. So the definition of potential is, it is if I take charge Q equal to plus 1 coulomb, then your potential will be equal to work done by external force in carrying charge from infinity to Q. So electric potential at a point is work done by external force in carrying charge and carrying unit positive test charge from infinity to that point against the field without acceleration. Against the field without acceleration. So this is the definition of potential at a point. Work done in carrying a unit positive test charge from infinity to a particular point against the field without acceleration is the potential at that. So this is the definition of potential. So after potential, due to a point charge. So this is the general definition of potential. This definition is valid for all types of charges. This is for all types of charges. All type of charges means you can have a point charge, you can have a non-point charge. For all type of charges, this definition is valid. You can do one more thing. See, although it's not given in NCERT, but in some numericals, you can use this trick. See, potential is work done by external force from infinity to a point P divided by test charge. Does any one of you remember the work done, the expression of work done in terms of field? How can we relate work done in field? Does anyone remember? It's an open question to all of you.
Can you repeat again?
Does anyone remember the relation between work done and electric field? I guess we did it today only. Huh? Relation between work done by external force and electric field. What's the expression? Yes, Saifullah. What's the expression of work done in terms of electric field? Noah? Minashi, what's the expression of work done in terms of electric field?
Minus QE into RP minus RA.
Yeah, minus Q integral of E dot dx. Right, Saifullah? This is the relation between work done and field. Na?
Yes, sir.
And what should be the limit of integration? You need work done from infinity to P. What should be the lower limit?
P infinity.
Lower limit should be infinity. Upper limit should be the position vector of P divided by Q. You can cancel this Q with Q and you are left with minus of integral of infinity the position vector of P. It's E. So this is again a relation between potential and field. That potential is minus of infinity to R P E dot. So that's the direct relation between potential and field. So if you know field, you can calculate potential. Just integrate field with a negative sign, you will get potential. But NCERT does not use this expression in derivation. For derivation, NCERT use this thing that first calculate work done, then divide that work done by charge, and then you will calculate the potential, get the value of potential. Otherwise, this will be easier. If you can do this thing, like you take field, integrate field, and you will get potential. Anyways, note it down. So for potential, always remember 3 points. First, it defines electrical properties of a charge, but it's a scalar function. It's not a vector quantity, it's a scalar quantity. Second, it's a property of a single charge. If you have 10 charges, that means you have 10 potential. Each charge will generate its own potential. And how you calculate potential? It's through work done. You calculate work done in carrying a test charge from infinity to a point Then you divide that work done by the test charge, and that will be the expression of work. Just note it down. See, this definition is very important. This definition is basically this thing. If you have work done, then take work done, divide that work done by the magnitude of charge, and you have this thing, potential. Okay, one small formula-based question. The formula-based question is on this relation. Small formula-based question. So in question, the work done is given and the magnitude of test charge is given. Is asking you to calculate the potential. Right? Question says work done.
सर एक मिनट ऊपर कर सर विदाउट एक्सेलरेशन का क्या है मतलब
Yes. See, this without acceleration is very important. If your charge without acceleration means net force on the charge is zero. It's moving with a uniform velocity, net force is zero. If a charge accelerates, then accelerated charge is a source of electric field. Accelerated charge is a source of electromagnetic wave. So if a charge accelerates, then that accelerating charge generates electromagnetic wave like light waves. So in your system, you will have light wave also. So we want to avoid light wave for the time being. That light wave will create issues in energy conservation. So if your charge starts accelerating, that will generate electromagnetic wave, like light waves, it will start generating. So system will have charge as well as waves, electromagnetic waves, light waves. So we want to avoid light waves for the time being. That's why we are considering charges without acceleration. Okay, before starting this question, let's write the SI unit of potential. The SI unit of potential, it's joule by coulomb. So it's joule per coulomb. Or you can write this as volt. It's joule per coulomb or volt. That's the SI unit of potential. Now, note it down. Write down this question. And write your answer in chat room. This is a straightforward thing. I'm expecting answers from each one of you. It's simply straightforward. Write down the question, note down the question, and write your answer in chat. What is the value of potential? Say I'm the host. Huh? Just send answers to host. Okay. Snowa is correct, Minashi is correct, Anshika is correct, Saifullah is correct. Mazia, Hishma, Yashika is correct. Alia. Yes, Hishma is correct. Mazia, Alia. See, this is a straightforward thing. Huh? You have work done, you need potential. So potential at a point B is work done in carrying charge from infinity to B divided the point charge. So work done is 20 joule. Your test charge is 2 coulomb. Just cancel them. You will get 10 joule. Alia and Mazia, is it clear now? Puneet?
सर मैंने तो भेजा.
Achha. So this is how we calculate potential. We need work done. Once you have work done, divide the work done by the magnitude of test charge, you will get potential. So let's do a few derivations. Mazia, is it clear? So electric potential due to a point charge. So this is a point charge. I need potential at P at a separation R from the point charge. So to calculate potential at P, what we do is we take a point at infinity. We take test charge at infinity. We need work done to bring this test charge from infinity to point. This is infinity. I take a test charge at infinity, and I need work done to bring this test charge from infinity to point. So the forces involved are variable forces. So what we do is we take a small path CD. It's dx. We first put test charge at C, and this test charge is at a separation x from cap. So first of all, we will calculate work done in carrying your charge q from C to D, and then we will integrate it from infinity to cap. So consider a charge q at a separation x from capital. So force on charge q is electric force on charge small q will be so electric force on charge small q is 1 over 4 pi epsilon naught. So it's q over x bar. This is electric force on charge q, 1 over 4 pi epsilon naught. It's q by x bar. So this electric force will act in this direction. This is the electric force. But I want to bring charge q from C to D. So to bring charge q from C to D, what we do is we apply an external force. So the external force to be applied on charge q. So the F external is this. F external is minus of F electric. So that's the relation between external force and electric force. The external force that you're applying is exactly opposite to that of electric force. So you can say that the magnitude of external force is equal to the magnitude of electric force, which is q over 4 pi epsilon naught x squared. That's my first equation. Now I need work done by external force to carry charge q from infinity to not infinity, sorry, from C to D. First, we will calculate work done from C to D. So work done will be dW. Only what will be the formula for work done? This is the external force. I'm carrying charge from C to D. Displacement is dx. What will be the work done?
So
Right.
F external into dx.
F external dot dx. Now this F external and dx are in opposite direction. F external is to the left hand side and the direction of dx is to the right. Dx is a small portion of this position vector. This position vector is acting to the right. That means dx is also acting to the right. So this vector and this vector, they're acting in opposite directions. So if they are acting in opposite directions, then the angle between them is 180 degrees. So F external dx cos 180. So you have cos 180 is -1. So you have minus of f external into dx. Let's call this as equation. Next, what we can do is we can substitute 1 into. So when we substitute 1 into, we get work done is minus of f external. It's minus of q over 4 pi epsilon naught x squared. This is work done for the small displacement. Then I need work done to carry charge from infinity. I need work done to carry charge from infinity to point P. So for this work done, we'll just integrate it minus q over 4 pi epsilon naught x squared dx. We are integrating it from infinity to P. The position vector of P is R. So integrating it from P to R, infinity to R. Your capital Q is constant, your small q is constant, your 4 pi epsilon naught is constant. This is infinity to R. You are left with just 1 by x squared dx. So you can write that work done is minus of q over 4 pi epsilon naught. The integral of 1 by x squared is x to the power minus 2 plus 1 over minus 2 plus 1. You can write this 1 by x squared as the x to the power minus 2. And the limit is from infinity to 1. So this is work done by external force. It's minus of q over 4 pi epsilon naught. X to the power minus 2 plus 1 is x to the power minus 1. Minus 2 plus 1 is minus 1. Limit is from infinity to 1. Negative and negative will become positive. So work done is q over 4 pi epsilon naught. It's x to the power minus 1, which is 1. Limit is from infinity to 1. So this is q over 4 pi epsilon naught. Instead of x, you can subtract 1 by r minus 1 by 1 by infinity is 0. So you can write that your work done is it's q over 4 pi epsilon. That's equation number. So if you have work done, that means you Yeah, sorry. So for potential, I was asking what is the relation between potential and work done, Mazia? Alia, what's the relation between potential and work done? We calculated work done in carrying charge from infinity to the point. How to calculate potential? Minashi, what's the relation between work done and potential?
Potential is equal to work done at infinity by Q.
So that's 1 by Q into work done, which is Q over 4 pi epsilon naught. So this Q will cancel this Q and you get its Q over 4 pi epsilon naught. So this is the relation between work done and potential. That potential is Q over 4 pi epsilon. So you can say that potential is inversely proportional to R. You increase R, your V will decrease. One more thing, potential is a scalar quantity. So if you have a positive charge, then your potential will be positive. But if you have a negative charge, the potential will be negative. So for positive charge, so if you have a positive charge, potential is positive. And for negative charge, it's negative. So this is the derivation. This is how we calculate potential for a point charge. Note it down. Yes, can I scroll it further? Is everyone have written up to here? No? This much you all have written. So that was the expression for potential due to a point charge. If you have a single point charge, then this is the expression of potential Q by 4 pi epsilon naught. The next is potential due to system of charges. Due to system of charges. So if you have a system having n point charges, let's say you have a charge Q1, you have another charge Q2, you have another charge Qn, and you're supposed to calculate potential over this point, R1, R2, R1. So what we will do is, we will calculate potential due to each of the individual charge. So the first charge, the potential is 1 over 4 pi epsilon naught. It's Q1 by R1. That is expression of potential due to the first charge. Ishma, what will be the expression of potential for second charge?
So 1 by 4 pi epsilon naught into Q2 by R2.
Q2 by R2. Similarly, we can calculate potential due to the nth charge. It's 1 over 4 pi epsilon naught. It's Q1 by R2. So for the net potential, what we can do is we can simply add them up algebraically. So the net potential is V1 plus V2 up to V. So this is how we calculate potential due to a system of n point charges. So this is simple, the algebraic sum. So when you do same thing for field, the sum is vector sum. That principle is known as superposition principle. But when you do the same thing for potential, just calculate potential due to each of the individual charge and add them up algebraically. Note it down. That's why I'm saying that potential is easier than field. There's no need of vector addition, just add them up algebraically. Written? Can I scroll it further? Yes, everyone. Written? See, there is one more relation, and that is the relation between work done and potential. Let's say you have a point A, the potential at A is VA. You have another point B, the potential at B is VB. I need work done by external force in carrying a charge from A to B. And that work done is Q, potential at B, minus potential at. So this is how we calculate work done by external charge in carrying charge from A to B. In terms of potential, it's Q VB minus VA. This is always work done by the external force. It's a shortcut method to calculate work done if potential is given. For example, if I give you a simple question, like if I say that VA is, let's say, 10 volt. VB, I say it's 2 volt. And I need work done to carry proton from A to B now. So to carry proton from A to B, the work done by external forces, it's the charge of proton into potential at B minus potential at A. So its charge of proton E, potential at B is 2 volt, potential at A is 10 volts, so it's minus of 8. This much of joule is the work done by external force. If I ask you to calculate work done by electric field for the same case, then work done by electric field is just negative of work done by external force. So that's minus of minus 8E, which is plus 8. This is it. Note it down. So the first type of questions that you will get on potential is, will use two concepts. One is the potential due to system of endpoint charges, and another concept would be the concept of work. So we'll first calculate potential, then using that potential, we will be calculating work. Okay, so written, Ishma, Mazia, Yashika.
Yes, sir.
Okay.
Yes, sir.
So that completes potential due to a point charge. We'll stop here. The next class, we will continue with some questions on this concept and the potential due to a dipole. On Wednesday, we'll continue with this thing. Now we can discuss doubts if you have. So class is over. If anyone have doubts, we can discuss those doubts at the end of the class. Sure. Okay, fine. If you have doubts, we can discuss them. Otherwise, you can leave.
Thank you, sir.
Okay, bacha. If anyone have doubts, we can discuss it